Next presentation is on sound devirtualization and LLVM by Peter and Chris.
Right, thank you very much.
Thank you.
So my name is Piotr, and today we are thrilled to tell you about most recent status of devirtualization and how we actually make it work. Okay, so firstly, what are the virtual calls? Virtual calls are a way to implement a polymorphism in object-oriented programming. It usually consists of three instructions, which is load of the vtable from virtual pointer. Then we need to load a virtual function from one of the slots of the vtable, and then we are just doing an indirect call on this on function pointer. And devirtualization is optimization that changes those virtual or indirect calls into direct calls. And it is pretty important for performance because, firstly, it gives much more opportunities for inlining. And second thing is that indirect calls are hard to predict for the CPU. And this is especially important with spectra and meltdown mitigation, which the red pollins pretty much disable the speculative jumps for indirect calls. And it also has some security implications because this is virtual calls are one of the vector of attacks. Okay, so let me tell you firstly about some of the optimizations that are currently done and that are pretty easy to handle. So for example, when we have a case like this is trivial to devirtualize in the front end because we know the concrete type, so front end will just change it to a direct call. If we require any inlining, like in this case, then of course front end cannot handle this because inlining is happening in the middle end. So in this case, if foo will be inlined and the constructor of A is visible and will be inlined, then LLVM should be able to figure this out and devirtualize the call. However, if there is any function call to any external function or function that we cannot reason about, then it won't be devirtualized. And this is because LLVM, or the optimizer, assumes that vpointer might be clobbered. So we conservatively need to assume that this function might have changed the dynamic type of an object, or like change the vpointer. So in this case, we will need to load the vpointer and do the indirect call. And if you think about it, it gets even worse because even if we would be able to devirtualize the first call, like in this case, if we weren't going to be able to inline it because it is in a different translation unit, for example, the second one won't be devirtualized because it also assumes the same thing about virtual functions, that the virtual function itself might have changed the dynamic type. So the basic idea behind our optimization is that we would like to mark vpointer as invariant. And using invariant load is totally sufficient for Java. Java is it is much easier to do devirtualization in Java because the semantics in Java is that, for example, we set vpointer only once in a most derived constructor, which is not the case for C++, as each derived constructor sets vpointer. And also we have things like placement new. So, for example, if you would create an object and then do a placement new on on this object, creating a new different type, then calling function on pointer b would be of course fine, but we cannot use the old pointer, although they are the same. But the semantics of C++ forbids us to do so. And it gets even more nasty because we could actually do the same thing. It is legal to do inside of the virtual function, so we can do placement new on this, and this would change dynamic type while like executing a virtual function. But the thing that is important to note is that if we would do so, then the second calling any virtual function on the old pointer would result in undefined behavior. So although placement new can do weird things like this, it is always safe to assume that if we are calling a virtual function on one pointer, then the dynamic type does not change. So for the old model, we introduced new metadata that could be put on the loads and stores called invariant group, which is very similar to invariant loads, but that can we can limit scope using barriers. And the barrier is intrinsic, that takes a pointer and returns a new pointer. And we would need to use it every time the dynamic type changes. And it would pretty much stop the invariant group optimization from happening. And the intrinsic returns a new SSA value. So basically what we try to do here is we try to use a new intrinsic to get us a new SSA value that, although would be the same as old one, it would somehow hide it from the optimizer, the fact that those are the same pointers. But from the beginning, we knew that there is a flaw in the model, which was we are trying to hide this fact from the optimizer, but we can actually expose it to the optimizer that the old pointer and the new pointer are the same pointers. And this code is legal in C++. Although we cannot use pointer A after doing placement new, we cannot dereference it. We can still use it for comparisons and like to see where it was pointing to. And in this case, we would miscompile and devirtualize the second call into a virtual function from A. And one of the solutions that we are thinking is like, okay, maybe we could add like barriers to comparison and stuff, but we knew that this is like somehow flaky, and it's either gonna stop the optimizer from doing some sort of optimization that you want to do, or it won't gonna work. Okay, and Chris is going to talk about a new model.
Okay, so instead of doing a mess of ad hoc fishy barriers, we started to think about some more structured model that was proposed by Richard, Chandler, and Sanjay. Is that we think of pointers to dynamic objects as somehow fat pointers, but only mentally. So we equip each pointer with an optional virtual metadata that it's not really there. It's both virtual as in sense of using devirtualization, and virtual as in sense it's not really there. We only imagine that it's there. And we require that each invariant group load or store must read or write, respectively, the value associated with the virtual metadata, so that basically the dynamic type of the object. And that comparison of objects' addresses or any other operations, such as pointer to int conversions that could possibly reveal the equality, must be done on raw pointers that have no associated virtual metadata. So at first we considered using an additional address space and using address space casts to perform this magic, but then we realized that it's not necessary. And we use plain pointers in LLVM IR, but we introduced two intrinsics. The first one is called Launder invariant group. It creates it gets a pointer and returns the same fat pointer with the same underlying group pointer, but with fresh virtual metadata. And we use it whenever the dynamic type could change. So, for example, in derived constructor and destructors, when we do a placement new operation, when we convert into a pointer, when we access a union member, because we could use placement new on unions and still reuse the old pointer. And its namesake stadlunder. And we also introduced a second intrinsic, which is basically similar. It strips the virtual metadata. So Launder returned a pointer with fresh metadata, and this one returns a pointer without any metadata. It's hence a it's a pure function, so it does not read any memory, so it can be optimized better. And we use it when we stop caring about the dynamic type. For example, when we do a pointer to int conversion or when we compare pointers. And it can be safely replaced with lambda. So any use of strip can be safely replaced by lambda, but it will hinder optimization. And those have some nice properties. If we call lambda twice, we can, so B is the lambda of A and C is the lambda of B, we can actually replace that C is lambda of A. We cannot say that C is equal to B because lambda is a stateful function. It could possibly returns a fresh pointer each time it's called. And similar for lambda and strip and lambda. And when we use a double strip, it actually turns out that strip is idempotent. So if B is the strip of A and C is strip of B, we can replace C with B. Moreover, the return pointer aliases the argument. As far as we know, the LLVM IR does not say that if two pointers alias each other and have the same size, they should be equal. It's not specified anywhere, it turns out, so we use this loophole. And both intrinsics can be removed if the result is dead. And why is the strip necessary? We can propagate equality through it. So in this example, when we compare A with A, we actually will compare strip of A with strip of A, which is equal because strip is a pure function. Moreover, it works even when the dynamic type changes. So here we do strip of lambda with just a strip, or things like strip of lambda. But those optimize to strip, which will be equal. And not only equality, but we can also propagate some other informations like pointers being less than each other and other relations between them. Probably modulo some minor bugs, but we claim that every information that could be inferred by the optimizer about pointers before our optimizations can be inferred about the strips afterwards. Okay, and I will yield to Piotr.
Thanks, Chris. Okay, so with the old model, we didn't see much of the improvement, but I gathered some results on how many virtual functions are actually get devirtualized by the middle end. And for LLVM, which does not use a lot of virtual functions, it was still like around 100% more like fully devirtualized calls. And the other numbers show like how much devirtualization we get and were not fully devirtualized. So, for example, we had 2 loads of vtables that were merged together, or 2 loads of one virtual function that got merged together. And for the chakra core, which is, I think it's a JavaScript engine for Microsoft Edge, it uses much more virtual functions, and we show even better numbers there. But of course, like, we care more about performance with this kind of optimization. So let's talk about benchmarks. So I ran some, during my last internship, I ran some extra benchmarks on the, with the Google infrastructure. And we see 0.8% improvement. So this is of geomean of all benchmarks. Each of these is a set of benchmarks of internal code base. And looking at some of them, for example, Plaque showed 4.6% improvement, which is quite nice, with some nice wins. And Protobuffers benchmark also, like, some of them showed even more than 30% speed up. And geomean was like 13% on one and 0.9% on the other. From other benchmarks, Google search engine speeded up by 0.6%. It doesn't mean that we speeded up Google search by 0.6% because they are using some more techniques like FDO and FinLTO, and we don't see as good improvement with those techniques because they actually do either like indirect call promotion or some other sort of devirtualization, because we enable, like we have more information. So we don't see as good improvement with those. But still, like 0.6% with O2 seems to be a very nice win. On the other hand, spec 2K6 didn't show much of a difference. And this is, I think, mostly because they are not virtual heavy. And of course, half of the benchmarks are C, so they don't even use virtual functions. Some compression benchmarks like 7-zip and zippy first it showed around 0.6% improvement, and this was before fixing a very subtle inliner bug, which was we treated our intrinsics as non-zero cost for the inlining. And after changing that, which is something that we wanted to do, we actually seen that they regressed or they were pretty much the same, while all of the other benchmarks speeded up. This pretty much means that, or we think that it means that the inliner is doing different decisions exposed to different thresholds, and in those cases it just happens that they are faster. But there is certainly something that we need to investigate further. Okay, so when are we getting the virtualization? There is only one thing that we need to fix before that, which is whenever we are doing any cross-module optimizations with functions emitted with the virtualization and functions that does not have like the virtualization enabled, then this could lead to some miscompilation because, for example, it wouldn't have those launders. And the way how we handle right now is that we just pretty much drop at during the link time. We say that okay, we cannot link those modules, and certainly this is not something that we want to do because this pretty much means that we wouldn't be able to do any LTO between like C++ and any other language. But RFC is coming soon. We think that we know how to handle this in a much better way. And we hope that with the next release, it will be turned on by default. And for some further work, there is a new experimental flag called -force emit vtables. This is different flag that right now this is different flag that enables actual the virtualization. The flag that enables the virtualization flag is fstrict-vtable-pointers. But this flag emits more vtables, and because as it turns out, Clang is very conservative of how many vtables it generates, and on the comparison, GCC is emitting like a lot of more information and a lot of more vtables, which makes like the object files much bigger, but it also enables much more optimizations. So we're looking into that to see if the cost pays. And there is also another very cool idea that I'm not sure who was the author, but I heard from Richard, is that whenever we are calling a virtual function from inside of the other virtual function, then we could specialize every virtual function to actually remove all those virtual calls inside of those virtual functions, because the only way how we would devirtualize it is we would need to inline it into another into the call site. So what we can do is we can specialize each of those functions, and this would mean that for some types that does not overwrite one function, we would pretty much duplicate the code and change the implementation to call different functions. And unfortunately, there is one more thing, because you can actually call a virtual function without doing a virtual dispatch in C++. And for this kind of case, we need to also emit a separate implementation that would do all the virtual dispatch inside. Okay, and with that, we're happy to answer your questions. Thank you.
I have a microphone, and there's a microphone in the center.
Thanks for the talk. Maybe just a quick comment. If you measure performance today, then the gain you get is from removing the call and then maybe doing more optimizations. But remember that there are things that make virtual calls more expensive, like red pollines or control flow integrity. It would be interesting to measure the gains from your devirtualization on top of those things.
Mm-hmm. Yeah, that's true. We actually I pinged Richard to run some experiments like 2 hours ago, and he ran to me like just before the presentation. And for the red pollines, it seems that there are certainly some wins with the devirtualization, but there are also some regressions that we will need to check out. So like in general, it was somewhere around like no change in geomean. Yeah, but like certainly like the red pollines is something that we care about because they disable the speculative execution.
Quick question. Have you measured the compile time and IR size increase due to intrinsics?
Well, we did. It turns out that some of our benchmarks in the LLVM test suite get longer compile times. Some of them get shorter compile times. There is no clear. There are no clear results.
Yeah, the results were like very noisy, and especially that we did some benchmarkings on some machines like Power that were shared, and with this we would see like 800% like either regression or improvement because like it was just too noisy and it was shared. So
yeah, but even on a dedicated ARM machine like a Raspberry Pi, we got some noise results.
Do you know about the code size?
No, I don't.
Okay, yeah, I don't think I like recall the numbers from the code size.
All right. Thank you once again, Peter and Chris.
Okay.